Okay. Okay. So, do you guys? What do you want to hear about? Should I just put up a list of important topics or something like that? Or I mean, the topics, the list of topics that I sent out. You know, some of them are bolded, some of them are italicized. It's kind of inconsistent. The ones in chapter 3, if it's bolded, it's important. The ones in chapter 7, if it's italicized, it's important, and then if it's bolded, it's super important. Yeah. Yes.
I just have like a quick, well,
Yeah.
I don't know if it's quick, but
Yeah.
a confusing thing that I've been thinking about is the difference between like a Cauchy sequence and then the Cauchy criterion.
Oh, okay.
Because like the Cauchy sequence
Yeah.
isn't necessarily convergent, but like the Cauchy criterion, which seems the same to me, means that it is convergent.
Yeah. Okay. Okay. So let's clear that up. What's the difference here? So so first off, we've got convergent sequences, right? Convergent sequence, right? So that just means, you know, that you have some sequence of points, and they converge to something. Means that you know, we can get them as close to P as we desire, right? We can get them as close to this point as we desire. Does anybody want to try putting out that definition, just to see if you, or write down what that should mean. Take a few seconds, write down what that means in, you know, the rigorous language. Okay, so let me just write it down. So right, here's P. So here's the picture, right? Here's P, and then the piece events, right, are heading towards it. And what it means is that you know, given any epsilon, there's a time past which everybody stays inside the. So there exists an n dependent on the epsilon, right? There's a time past, you know, for each epsilon, there's a time past which you end up in that epsilon circle, right? So given any epsilon, there exists a time dependent on epsilon such that if you're past that time, then you lie within the epsilon ball, right? So you're inside the epsilon neighborhood of P. Right? In other words, the distance between you and P is smaller than epsilon. Okay. Now, there's Cauchy sequence, which is a different idea, right? So you have, again, you have P sub n. It is said to be Cauchy if, now this is different. So this means that, right, given any epsilon ball, given any epsilon, so there exists a time dependent only on epsilon, such that if n and m are past that time, then the distance between Pn and Pm is smaller than epsilon. So this is a little bit different. The picture is a bit harder to grasp, right? Given any epsilon, right? So you're given some distance, right? And then there's a time past which everybody is within epsilon of each other. Everybody is within epsilon of each other. So, you know, in particular, it means that if you take any one of them and take the epsilon ball, right, then everybody past there is inside there, right? So the PM is going to be inside there. But also, you know, conversely, for the PM, if you take the epsilon ball, you know, I guess it's kind of obvious. Anyway, so, but these are not the same things, remember, right? These are not the same things, okay? But in complete spaces, they are, right? So equivalent, if it's equivalent, so if these are equivalent, then the space is complete. Okay, in particular, R is complete, C is complete, right? Okay, so now, the second idea. Okay, so now we're talking about, say, like the limit of a series of, say, complex numbers. Okay, limit of a series of complex numbers. Okay, so something like this, C sub n. Okay, and or maybe I should say convergence of a series. Of a series of complex numbers, right? So that, what does that mean? Means that, right, to some value, capital C. Okay. So what does that mean? That means that that the sequence of partial sums S sub n, which is defined as the sum of the C sub k from k equals 1 to n, converges to C. Right? Right? And that means in, using, so it's the convergence of a sequence, right? That a sequence converges, right? Convergence of a sequence means that, right, given any epsilon, there exists an n dependent on epsilon, such that n bigger than n implies that S of n minus C is smaller than epsilon. Okay, but these are complex numbers, right? This is a complex series. This is a sequence of complex numbers converging, right? And the complex space is complete, right? The space of complex numbers is complete, and so so since C is complete, this thing down here is the same thing as saying that, so this thing here down here is the same thing as saying that S of n is Cauchy. Right? Okay. And so this gives us the Cauchy criterion, right? So gives the Cauchy criterion, which is just translation of this statement, right? S of n is Cauchy, right? S of n is Cauchy means that, right, given any epsilon, there exists an n past which the distance between Sn and Sm, so that if n and m are bigger than n, then that this thing is smaller than epsilon. Right? Okay. And what's this thing? This thing is this is the sum up to m minus the sum up to n, right? This is the sum to m of the ck minus the sum to n of the ck, right? So that's the same thing as the sum from n plus 1 to n to ck of ck, right? So that's the Cauchy criterion, right? So so to have i.e. this thing from n plus 1 to m is smaller than epsilon. Right, so that's the Cauchy criterion, and normally because we could just subtract 1 from the n, so we write it like this, right? That plus 1 doesn't matter at all, right? Because we can take a slightly larger, we can take a smaller n or something like that. Yeah, it doesn't matter. Okay, so yeah, so that gives the Cauchy criterion, right? And that's pretty useful. Right, that when you want to see if a series converges, that's the same thing as checking if you can make the partial tails small. Right. That convergence is the same thing as saying can control size of partial tails. Okay, and then that thing, translated into the world of like convergence of functions gives us Cauchy criterions for pointwise convergence, Cauchy criterion for Cauchy criterion for uniform convergence, et cetera, et cetera. So maybe just to illustrate. Right. So, stepping from the world of points to the world of functions. So if we think, for example, of the important uniform convergence of a sequence of functions, right? Remember, we say Fn converges to F means that, Fn converges to F uniformly means that right, we can get everybody inside the tube. Right, we can get everybody inside the tube. So right, given an epsilon, exists a time such that if n is bigger than n, then f sub n x minus f of x is smaller than epsilon for all x in our set. Right, that's uniform convergence, plain old uniform convergence. But we can, we can translate this to Cauchy criterion, right? So Fn using the Cauchy criterion, this thing converges to that. Means that for all epsilon greater than 0, there exists an n such that if n and m are bigger than n, then Fn minus Fm is smaller than epsilon for all x in epsilon, f of x in e. Okay, so so all these things about convergence. As long as it's a statement about, these guys are complex value functions, right? As long as we're doing a statement and what we're saying is something about a complete metric space, we can say, well, that's the same thing as checking the Cauchiness of it, right? So we can change the requirement into a Cauchy requirement. So does that clear
Yeah.
things up? Okay. Yeah, those are, yeah. Yeah. Kaylin, how about you?
I don't have questions right now.
Okay, okay. Julia, how about you?
I don't have questions right now either.
Oh, okay, okay. Well, Charlotte, do you have other things you would like to talk about, or?
I haven't actually looked over at the.
Okay, do you guys want to take a look at the list, maybe? And,
Maybe Anne has questions.
yeah, and do you have anything you'd like to ask about?
I'm still a little shaky on equicontinuity.
Equicontinuity, yeah, yeah. Let's see.
Weierstrass M-Test.
Yeah. So, maybe let's just remind ourselves first what equicontinuity means. So it's just uniform continuity, right? So you've got a family. So you have some family functions, right? And it's called equicontinuous. If, right, so given any epsilon, right, for any epsilon, there exists a delta that depends only on epsilon, such that if your 2 points are closer than delta, then your output points are closer than epsilon. Right? And this is for all x and y in your, so from x to y, so metric spaces. So for all x and y in your domain, and for all f in your family, right? So that just means, right, that they're uniformly continuous, right? Right, that they're uniformly continuous, but in a way that where the delta doesn't depend on even the function. Right, the delta depends on epsilon only.
Okay.
Okay, so that's what that means. Maybe let me see if I can find a problem that that will be helpful. I think this one is probably a good one. Okay, so this is number 15. You have f, a function from R to R, and it's then you create a family, Fn, defined as f of nt, n equals 1, 2, 3, etc. Okay. And the family is equicontinuous. Okay. And then they say, what conclusion can you draw? Then what? So if it turns out that that family is equicontinuous, what would that tell you? What would that tell you? So, let's think about that. So, right, you start off with some function, right? So let's say your function goes like this, right? And then you're looking at sort of sped up versions of that function, right? For these guys, the time is moving, at the same speed for the first guy, and then twice as fast for the second guy, 3 times as fast, 4 times as fast, et cetera, right? So everything gets compressed, right? Everything gets compressed here. So like whatever has happened in this period is going to happen here, right? So it's going to go like up, down, and then it's kind of hard for me to draw. But anyway, times gets compressed. Right? Okay, and we're saying that everything is equicontinuous, right? They're equicontinuous. So, right. So, what does that mean? That means that given any epsilon, right? Given any epsilon, we can find a delta so that the values don't vary by more than epsilon, and that happens for everybody, right? So for every one of those functions, so let's just choose some. Let's just choose some distance. Okay, just in this imaginary picture, let's choose an epsilon of 1. Okay, so for this epsilon of 1, what we're saying is that we can find for the whole family, right? Actually, let me just let's make this even simpler. I'm gonna just do this function here. There it is. Okay, so there it is. It's f of x equals x on 0, 1. Okay, so I'm just chopping it off there, right? So f2 is going to look like this. f3 is going to look like this. f4 is going to look like this, right? It just gets squashed. Okay. Okay. So let me ask you this: is f sub n? Are these f sub n's equicontinuous? These guys equicontinuous, right? Equicontinuous should mean that we can find a delta, so that within that delta, right? Within that delta, everybody moves less than epsilon, right? Suppose we just look at the first 2 guys. Okay, this guy and this guy, and I say, I'm going to give you an epsilon of a half, say. Okay, epsilon of a half. Okay. Well, can you give me a delta so that nobody moves more than a half within delta? Let's just do it with one function first. Can you give me a delta so that as long as the 2 points down here are within delta of each other, the outputs are within a half of each other? Sure, right? Right. Just take delta to be 1/2, right? As long as these guys are within a half of each other, the outputs are going to be within a half of each other, right? Okay. Now I've got the second one. I throw that guy in. I say I want a delta that works for both of them, right? What delta should I choose now? A quarter, right? Because this guy has a slope of 2, right? Right. So you choose a quarter, right? So that'll work that delta works for everybody here. Okay. So this family here of just these 2 functions, they're equicontinuous, right? Okay. But now what we're saying is that we're gonna take all sped up versions of this function, right? Is this family equicontinuous? No, right? There's no way you're gonna find, if I take a delta of a half and I say, I want a delta that's gonna work for everybody, right? Well, right, like, let me take a delta that's, I'm sorry, let me take an epsilon, not a delta. Let me take an epsilon that's just slightly less than 1. Okay. And I say, I want you to find me a delta so that as long as two guys are within delta of each other, then the outputs are within epsilon of each other. Well, the trouble is that these slopes become arbitrarily high, right? The slopes become arbitrarily high, and so I can choose, no matter what delta you choose, there's going to be some function that within, if I look at this interval here, if I look at this delta neighborhood here, there's going to be some function that jumps out of there, right? Because I just have to choose a slope that exceeds this bar within that time frame, right? Okay, so this is not equicontinuous. Okay, so let's think again. Like, suppose we have a function, and we just have some arbitrary function, right? There's some arbitrary function. It has some values. Okay, right? It has some values. I'm not even going to draw up the other values. Okay, it's got these two values. Okay, and it's got the times. We're looking at the time speed up family, right? Well, you see what's going to happen, right? What's going to happen here? Could this family be equicontinuous? You can tell by my tone of voice that the answer is no. Right? Why? Why not? Why can't it be equicontinuous? And
Well, because they're speeding up, the slopes are just.
exactly,
Yeah.
same problem. So exactly the same problem is going to happen, right? We've got these two values, and then as time speeds up, these guys are going to get closer and closer, right? The inputs are going to get closer and closer, right? And so if I choose an epsilon, right, that's smaller than the difference, if I choose an epsilon that's smaller than the difference, at some point, right, no matter what delta you choose, well, at some point, you're gonna have some point over here, and then some point over here, and they're gonna be within, yes?
Oh, sorry.
Yeah.
I was just gonna, so would that mean that has to be constant?
They have to be constant. Yeah. So the only way this could happen is f is constant. Okay. I hope that gives you better like a more visceral feeling of what equicontinuity means. You have to be able to find a delta that works for everybody, right? So, right, so your family can't become arbitrarily, the slopes of your family can't become arbitrarily great, right? If you're looking at differentiable functions, then, well, I mean, at least the opposite is true. If you know that the slopes are under control, then you know that your family is equicontinuous, right? And not being equicontinuous means basically that things get kind of out of control with regard to how far you jump within a certain time frame. Okay. Anyone else? Anybody see something that they wanted to hear about?
I have another one if that
Yeah,
helps
sure.
us.
Yep, go ahead.
The Weierstrass M-Test.
Yeah. Mhm.
I remember doing it, but I'm a little.
Sure. That's super important. And so what that says is that if you have a series of functions, okay, so you have a series of functions and they're complex valued. Okay. Got these complex valued functions, And you want to find out if this thing, so basically it's the answer, the question is, when is this thing, no, it's not really that answer, but basically, Weierstrass, the M-test gives conditions that imply that this thing is uniformly convergent. Okay. That's the significance of the M-test, right? That what's it good for? It gives you these things that you can check, and if they're satisfied, then this guy is uniformly convergent. Uniformly convergent is useful because, for example, you can do term-by-term integration, right? We saw that you can, if you take the integral, you could take, when you're taking the integral of this infinite sum, you can actually do it as a sum of integrals. You can integrate each one of them separately, right? So yeah, so that's really important in complex analysis. Okay. Okay. So the conditions are that. What are the conditions? The conditions are that that these guys be bounded. So they all have to be bounded, and the sum of the bounds has to be finite. Right? The sum of the bounds is convergent. Okay. So. I think one of the homework problems was something along the lines of show that x over, no, I don't remember. Sorry. Anyway, so do you want to see the proof of this, or is it proof, or do you just want to know?
I mean, I guess I don't fully know how you use it in application. Like, I remember doing them in the homework, but
Okay,
I feel like that
okay. Yeah, let me see if I can find the problem that was relevant. Oh yeah, here's one. Okay. So, let's see. This is number 8. And we have a function I of x, which is 0 up until x equals 0, and then it's 1 afterwards. So it's the so-called Heaviside function. Heaviside step function. Okay. And then you've got a bunch of points, so xn are distinct points in AB, and you have a bunch of coefficients such that the sums of the absolute values converge. So the claim is that the sum of the shifted Heaviside functions multiplied by these coefficients converges uniformly. Okay. Okay, so the picture is that, right, you've got these points, right, x1, x2, x3, xn, got a bunch of points in some interval, a, b. And then you've got these shifted Heaviside functions, right? So at x1, right, you've got this guy, it basically stops here and then jumps up to 1, right? And you've got that guy at x2, x3, x4, et cetera, right? You've got, in fact, you've got infinitely many of them. Okay, you just keep on going. Okay, and you've got these coefficients too. So you multiply each of these guys by some coefficient. Okay, and you add them all together. Okay, you add that infinite series together. So you take all those functions, you scale them, you add them all together, and you want to show that that converges to something. Okay. So you just say, well, Weierstrass M-Test. Weierstrass M-Test, right? Because Weierstrass M-Test says that as long as the functions are bounded and the sum of the bounds is finite, then you've got uniform convergence, right? So let's just check, right? So the answer is use M-Test. And if you were like gutsy enough, you would just stop your proof right there, just saying use M-Test. If you don't mind me telling a story, there was a student back at Princeton who was like seen as like the genius among geniuses. Like he finished his degree at Princeton in 3 years, and then he was asked to, he was allowed to pursue his PhD there. And normally normally institutions don't accept their own students to their graduate programs. It's some sort of rule, like you don't accept your own students. But in this case, they let him continue as a PhD student. And it's my understanding that he finished his PhD in 1 year, and then left. He's now a professor at Kyoto University, and he's published some work that apparently nobody can understand. It's like beyond. He's answered there's some conjecture called the ABC conjecture. ABC conjecture, and he has like created this whole series of papers that apparently nobody can understand, where he proves the ABC conjecture. And so it's a little bit tricky because like nobody can understand what he's done. So has he really proven it? But given his reputation, you know, people believe that he has done it and are just trying to understand what he's been talking about for 10 years. Anyway, you know, so he was I think a year or two ahead of me at Princeton, and we heard that he was held in such respect by everybody that on the homeworks he would just write, "This is trivial." That was his answer. Like here's the problem, and he would just write, "This is trivial," and he would get full credit for that because yeah, they recognized that for him it actually was trivial. So yeah, Shin Mochizuki is his name. Shin Mochizuki. Yeah, I didn't know him. He was just sort of this legendary, you know, upperclassman. Yeah, there were other sort of legendary things. Yeah, like Nash was there. Do you guys know the name John Nash? Right? There's a movie. They made a movie about him called A Beautiful Mind or something like that. Nash, you know, one of the great mathematicians in the mid 20th century, I think. But he eventually descended into schizophrenia, and so we didn't know anything. This was well before the movie was made, and so all we knew was that there was rumors of a professor who had gone mad, right, and would just wander around the basement of the math tower, and would write things. Well, the story was that he would go to a board, he would write something on it, and it was always the same thing, and he would stop there, you know, smile a little bit, and then leave. So, yeah, but yeah. So Nash, you know, sort of a super genius in you know, who sort of like stuck his hands into completely different fields of mathematics, and like would go into a field, just like prove the hardest thing there, pull out of it, go to the next field, prove the hardest thing that there was the hardest, you know, unsolved problem, and then just. He was awarded the Nobel Prize in Economics for something called Nash equilibrium, but that in terms of his mathematical work, is sort of considered like a side note or like a very minor thing that he did. Yeah, it's kind of fortunately he actually came out of his schizophrenia. If you read his biography, it seems to be due to the kindness of another professor, Hale Trotter, who we did know, and he was a very nice guy, and he gave Nash access to the computers at Princeton, and Nash really got into programming, and somehow, like his ability to kind of control and master something allowed him to recover his sanity. So that's a really kind of cool story that this act of kindness brought him back. Yeah. And then after that he was awarded the Nobel Prize in economics. Okay, so the M-Test, right? So what does the M-Test say? It says, well, look at each of these functions, right? Look at each of these functions, and are they bounded, right? Right. So like if we look at each of these guys, right? Well, this is just the size of Cn times the size of the function, right? The size of the function is 1, right? This value is either 0 or 1, right? So this is smaller than Cn, right? So this is the bound, right? And then you check that the sums of the bounds converges, but that's given to you, right? The sum of the bounds do converge, right? And so you know that this thing converges uniformly, right? That's it. Okay. And I think the second part of the question is to show that you have continuity, that this infinite sum converges. I'm sorry, that this infinite sum is continuous at every other point other than these points. You've got continuity. Right, and that's true because if you're looking at some other point like P here, so not one of the xi's, not one of the xi's, well, all of these functions are continuous at P, right? The only things are, this guy's discontinuous at x1, but it's continuous everywhere else. This guy's continuous at x2, but it's continuous everywhere else, right? So at P, everybody, if P is not among the xn's, then all these guys are all continuous, okay. Right? And so we have a uniformly convergent sequence of functions. We have a uniformly convergent series of functions, each of which is continuous. And so we have that theorem that says that uniform convergence is going to guarantee that continuity is preserved. Right, so you're guaranteed that it's going to be continuous at any point other than these distinct points. I realize I haven't told many stories this semester. Normally I tell loads and loads of stories. Sure. Anyway, let me think of one. Okay, here's a joke that my TA told me in my first year at Princeton. I forget, it was in the first class or the second class. So it's a joke, sort of like a apocryphal story about the mathematician Norbert Wiener at MIT, an analyst. He was kind of, again, sort of an eccentric. They said that it said that he would walk to his classrooms by placing his hand on the wall and then just walking, and because he knew that eventually he would end up at his classroom. It was such that his classroom was such that as long as he kept contact with the wall, he would eventually end up there. And so he would do this so that he didn't have to think about where he was going. He could think about mathematics while he was just walking, as long as he kept his finger on the wall. Anyway, so the story is that he was such an absent-minded person that let me make sure I get this right. Okay, so one day Norbert Wiener's family moves, and being the absent-minded professor that he forgets that he has moved. Okay, and he goes back to his old house. He's like, there's nobody here. Why is there nobody here? The house is empty, right? And then he notices a little girl sitting sitting nearby, and he goes up to her and he says, "Little girl, can you tell me what happened to the family that lived here?" And she says, "Mommy told me to wait here for you." Daddy. So he didn't even realize, he was so like focused on the problem, he didn't realize that it was his own daughter that he was speaking to. But this is really just an apocryphal story. I saw in a magazine article that they spoke to the daughter of Norbert Wiener, and she said that never happened.